Right, good morning everyone. Morning. So this talk is about a project that I've been involved with for the last year, and you may notice that at the last LCA I was carrying around this little gizmo and playing with it. I'm often obsessed with new little bits of electronics, new toys, and so I had this connected to my laptop during some of the talks, and between times it's a little autopilot. It's called an Autopilot Mega APM-1 Autopilot. I was just really starting on the project that I'm going to talk about today, and I've been working on this project for the last year, and it's been quite a wild ride. I've had to learn an awful lot about microcontrollers and avionics and autopilots, lots of things. So I'm going to try and give you a bit of an overview of the project, what we're doing, what we're trying to achieve, what we've achieved so far, and what we're hoping to achieve through the rest of this year. So the aim of this project is to find this guy and rescue him. So this is Joe. Now Joe got lost in Queensland near Kingaroy a few years ago, about 4 years ago, and there have been teams from all over the world trying to find him in those last 4 years. No one's yet actually managed to rescue him, so we're hoping that our team will be the ones to rescue Joe this year. And there's a competition where the teams get together in September up in Kingaroy, and you have to bring an aircraft, a rescue aircraft, and you're trying to rescue this guy. Now this guy, of course, he's a lost bushwalker, but he was very well prepared. He's got a 50-watt IR source next to him. All bushwalkers should carry one of those. A nuclear generator to run it for 4 years. And he also is on Twitter, so he's a very well-connected lost bushwalker. So this is the Outback Challenge, and the basic idea is to search for this lost bushwalker near Kingaroy in Queensland this coming September. This year there are currently 53 teams from 10 countries participating, and most of them are from Australia, but there are 10 other countries involved, 1 or 2 teams from Canada and various places in Europe, all over the world. What you're trying to do is find Joe in this little green box here. There's a little green box there, which is 2.2 kilometres by 1.2 kilometres. The actual coordinates may vary on the day due to local conditions, but that's roughly it. You take off from up the top here, where the airfield is marked, the little aeroplane icon, little green one. You take off there, you have to fly about 5 or 6 kilometres to the search area, and then search that search area, find Joe. Once you've located him and the organisers have confirmed the position, you need to drop him a rescue package, which is simulated by a water bottle. So we have a water bottle like this, and we need to drop it from our aircraft and not hit Joe. If you hit Joe, you get no points, but if you get points based on how far away from Joe, the closer the better, without actually hitting him. And anyways, that's the idea. Automation is the key. You have to, at minimum, do completely automatic flight. So you have to have an autopilot, you have to do automatic navigation, you have to have a lot of other automation. Some pieces of the automation are optional, and being gluttons for punishment, because this is our first time in the competition, we decided to go all the way and do complete automation. So we're hoping that in September we will press a button and the plane will automatically take off itself, fly to the search area, search. Onboard computer systems are going to be doing computer vision, analysing the photos that it takes about 8 frames a second of cameras over the area. It'll be several thousand photos it'll take over the period of time of the search. Onboard computer systems will analyse those images to find what looks like Joe, a human, on the ground. Will automatically geo-reference those positions that it's found and add up the probabilities from thousands of frames to find the most likely location for Joe, communicate that back to the organisers, get the okay for a bottle drop, work out the trajectory for the bottle drop, do the ballistic drop so the bottle drops as close to Joe as possible, fly home, land, and see us quivering in a heap on the ground as we were nervous for that whole hour. So that's what we're hoping to do. So there's a lot to this. We thought in the meeting when we first sort of got started on this. Oh, this looks fine, this can't be too hard. There's an awful lot to this, and originally the competition was going to be held last September, and the organisers decided that they would give people 2 years to prepare this time rather than 1 year, because they found teams weren't well enough prepared. Very few of the aircraft even got to the point of taking off in the previous competition. So this year you've got 2 years. We thought, oh gosh, we would have been ready. No way. We wouldn't have been ready for last September. In fact, we're thinking, do we have time for this September? You know, more than a year and a half to prepare and actually put in a good showing. It's a really difficult task. And if we achieve this task, once somebody has achieved it, well, there's a nice bit of prize money and things, but then the organisers will make it harder the following year. And the idea of this competition is to promote the development of civilian, not military, civilian search and rescue applications for unmanned aerial vehicles cheaply, to create the technology available to everyone, so hopefully in the future your rural fire service or your SES local brigade, those groups will be able to afford this sort of civilian UAV technology to really rescue someone. Because this sort of technology, it's used by the military all over the world, but it's not accessible in a packaged form that can do this sort of complete task to civilians. Okay, so in that vein, we decided to be a completely open project. This is one of our early meetings. We've now got a lot more people in the team. In fact, we've got another team member, Amitay Isaacs, who wants to put his hand up. Amitay, where are you? There he is down there, is another team member. So we've got a whole lot of people in our team. Quite diverse range of skills. We've got people with long experience in aero modelling, building and crashing radio-controlled planes. Amateur radio people, we've got ham radio people, and we've got electronics specialists, computer vision specialists, software engineers, a whole lot of people involved in the project. And it's been a real pleasure being involved with so many talented people in this team. We decided, contrary to what most teams in this competition are doing, to be completely open. Our mailing list is open, all our code is in public repositories, all of the schematics for the electronics we're building are completely open, because we thought that the best way to promote the creation of cheap civilian UAVs for doing good, for search and rescue and other applications, environmental monitoring, etc., is to make everything open so that everyone else can benefit in the future. We've got affiliations with various other groups. The Canberra Model Aircraft Club, you can see down the bottom right there, this is our local flying field in Canberra, a beautiful flying field. That's a pilot standing down there, that little tiny figure, which you probably can't see. And then we also are affiliated with the Dickson College Schools team. There's a schools competition each year, which was held last September, and the Dickson College team entered and had a lot of fun in that. And the Make Hack Void hackerspace, which is where the whole group got started. I think it was my first Make Hack Void hackerspace meeting where I said, hey, that looks like fun. I'll join in the UAV project. Okay, so here are some of the technical challenges in this project. We've discovered just how hard it is to do all the tasks involved. You need to build a good airframe. You're not allowed to, in the competition, just use a complete package, airframe, avionics, the whole thing all done. You do have to build something. You don't have to do a scratch build. You can use a commercial airframe, but then put all your own electronics, etc. in it. Autopilots, amazingly complex to get autopilots right. The thing needs to fly for an hour or so accurately and needs to cope with high wind conditions, lots of things like that. It's quite complex building a good autopilot. Navigation issues, planning and execution of navigation. Accurate sensors, we spent a lot of time on sensor libraries. Huge array of sensors is on the plane. I'll go through some of those sensors later in the talk. Reliable radio links. The radio link we originally thought would be, not too hard. I mean, it's easy enough to get radios that can do long distances. In fact, radio is a very interesting problem to have a very reliable radio link. And in the context of this, you need to remember that the organisers have some extremely strict rules in this competition. Great thick booklet of rules. And if you lose radio link, for example, for more than a few seconds, then you have to take specific actions. You have to, for example, turn back or initially loiter for a certain fixed period of time. After you've loitered for a period of time, you have to then fly back to a radio point where you try and re-establish radio contact. And the plane has to do this all itself because you've lost contact with the plane. And after it's reached that point, if it doesn't re-establish radio contact, the plane has to either fly home and land itself or it has to crash itself. And crashing itself is something that we're really hoping to avoid, but it is something that is very much on the cards for this competition. The rules are quite explicit about the safety requirements. The insurance for the competition covers the planes flying in a very specific area. If there's any chance at all that it might be flying outside of that area, you lose GPS, you hit a boundary, the plane is required to smash itself into the ground. And you have to demonstrate that works. Won't that be fun? Machine vision, so we have to have cameras, and I've got down here a couple of the machine vision cameras that we're using in a little box. These are cameras that are normally used to control robots in a factory. They're extremely sensitive cameras. We're typically taking sort of 50 to 70 microsecond exposures on these cameras. That means that vibration is much less of a problem than it might be for the cameras at least. We have camera control, keeping the camera stabilised, pointing at the ground, that sort of thing. Ground station, you need control, you need a ground station that's going to work out in the sunlight, and you need lots of software on the ground station to monitor and control the aircraft. We've put a lot of effort into our ground station software. Vibration control is rather important, and vibrations are an absolute curse for UAVs, and you need to seriously look at exactly how you're controlling vibrations. If you don't control vibrations extremely well, then you can get some rather erratic drifts in your attitude solution. The plane can go wildly off course if you have vibration, giving aliasing at the wrong frequency. So you really need to be very, very careful about how you control vibration in your aircraft. Okay, so now I'll just run through some of the aircraft we've been using. So this was one of the early aircraft. Those of you who've flown radio-controlled planes, how many in the audience have flown radio-controlled planes? A few? Excellent. How many have flown a UAV? Any UAV people? A couple of people. Excellent. Anyone else here, by the way, entering the competition? Any other competing teams here? Thought there might be, because I know there's quite a few sort of hackerspaces that are involved. Okay, no other competing teams. So this is a little thing called a Skywalker, which is a cheap plane, $100 airframe, $200 with all the basic electronics, servos, ESC, that sort of thing. It can fly for about an hour on a 4-cell, 5 amp hour LiPo. And this was one of the early planes we tested our camera and avionics electronics in, Autopilot and the onboard computer system. It was a very, very useful initial test plane. It flies very slowly. It flies typically 12 to 15 metres per second, and it's extremely easy to fly. It's a very popular plane for long-distance FPV, first-person view flying, where you have goggles on and you have a little camera on the plane and you're in the pilot's seat as you're flying it along. Very popular plane for that sort of thing, and it was a useful plane. This has been our main workhorse for testing of our systems. It's called a senior Telemaster, and I got this second-hand from another club member at CMAC. It's a model that's been around for a very long time. I think the design is about 40-odd years old, a very old model. It's an 8-foot wingspan. It weighs, with our electronics, just under 7 kilograms. This one is electric, that very often has a petrol motor or a nitro motor in it. And we get about 30 minutes flight with a 10 amp hours 4-cell battery on board. And that's extremely useful for the stuff that we're doing. So most of our imagery has been taken on this plane. This plane does not fly for long enough for us to use it in the competition, at least with our payload. One of these planes, a senior Telemaster, was used to great success in the 2009 Outback Challenge, and in fact it got the top score in the challenge. Didn't find Joe, but got the highest score, so it was the winner for the year. but we've got a lot more electronics and things on board, and with the extra weight, we wouldn't actually get the flight time on this to be able to complete the challenge, unless we got lucky and found Joe early and were able to come back early. So, this is the plane that we're currently planning to use for the competition. This is called a Mugin, also known as a CyberHawk. It's a 3-metre wingspan, 20 kilogram takeoff weight. It's got a 50cc petrol motor, and it will fly for somewhere around 3 hours or so on a tank of gas, petrol about that big. So it's a fairly serious UAV. It's not the sort of thing you can just throw in the back of the car easily. You really need a big van or a station wagon or something. It takes us about an hour to get it ready to fly. It's fairly fiddly, putting all the servo cables and through. The photos there really doesn't do it justice. It really is quite large and plenty of room inside it for avionics and all our cameras and that sort of thing. To give you an idea, up the front of the aircraft there's actually 4 kilograms of lead acid batteries that aren't connected to anything. That's just the ballast so that it is the centre of gravity is in the right position. So imagine 4 kilos of great big lead acid batteries just as ballast wide into the front. So it's a relatively large size. It's called a large model in the aero modelling community. So that's our main airframe. We've also had some other test aircraft. For example, early on I bought myself a little Arducopter quadcopter with the rubber duck. Anyone recognise that rubber duck? Oh yeah. Yeah, from Brisbane. So that's one of the rubber ducks from Brisbane, and I use that. Oh, anyone know why I would have a rubber duck on the top of my quadcopter? Know which way's up? Yeah, more which way's forward. The nose of the duck points forward. Because in a quadcopter, it's rather difficult to see which way's forward, and you get confused about which way it's going to go. There's ways of solving that with the autopilot, but bottom left there's 2 planes there. There's a Boomerang and a Dragon Lady, and you can see there David Woodgate, who's one of our team members. He's a radio specialist, but he also works a lot on the bottle drop mechanism, and you can see he's making an adjustment to the bottle drop mechanism for dropping the bottle to Joe. That's a nitro plane. The plane in the top right corner is unfortunately the same plane as the one that David is looking at down there, and that was after an unfortunate incident. That was the first attempt to use the autopilot on the Dragon Lady, and unfortunately we had poor settings on the autopilot. We had some dip switches set so that it thought it was an elevon plane, and elevons are different from ailerons and elevators and rudders, and it dived itself into the ground very rapidly. So we've made lots of mistakes and we've lost planes as a result. This little plane in the bottom right corner is a Skyfun. It's the only one I could fit in the car to bring down from Canberra, so I brought it along today in case people want to have a closer look at it. And it's a little delta wing plane. I'm using this partly for testing autopilot stuff, geo-fencing that I'll talk about later in the talk. But it's also quite good for teaching me to fly, because we need a couple of Goldwing pilots. We actually do have 2 Goldwing pilots in the team now. Goldwing pilots, there's a thing called the MAAA, Model Aircraft Association of Australia, and in order to be in the competition you have to have a certain level of qualification, and I've currently got my bronze wings. I'm aiming to get my gold wings. This sort of plane will hopefully teach me a bit of the sort of aerobatics you need to be able to do in order to get up to gold wing standard. But otherwise, we've already got a couple of other people in the team who've already got their gold wings. I'll fire that up later so you can have a look at how it does stabilisation. So there are sort of additional test aircraft. There's 2 or 3 other test aircraft we've got in our hangar that we use for more specialised purposes. So this is a rough idea of what the avionics, the electronics on board the plane look like. We have a radio receiver, RC receiver in the top left corner there, which in this little one here, that would be that little black box there, right? That receives the radio control for when we've got manual control from a RC transmitter like this. This transmitter, by the way, runs open source firmware, the ER9X firmware, really nice. Dirt cheap transmitter, $59 you can get the transmitter for, compared to many hundreds it usually cost. And the firmware on the default transmitter is complete crap, but if you load the open source ER9X, it's brilliant. So a lot of our stuff is free software, and I've always pushed towards using the free software things if we can in the competition. RC receiver goes into a little fail-safe controller. That's an Arduino 328. That's, you need to have a fail-safe controller for the rules of the competition. It basically monitors whether you're obeying the rules of the competition, and if any of the rules are breached, even for a short period of time, it controls the servos on the plane, and the competition rules specify that you must put the rudder hard over, the elevator hard up, and the ailerons hard in opposite directions. And what happens when you do that to a plane, you go spiral straight into the ground. And once you're into that mode, you're not allowed to come out of it. So basically that's the safety factor to ensure that planes don't get flyaways, because a 20 kilogram plane with a carbon fibre propeller that long with 50cc motor, if that ran into somebody's house, then hit somebody, that would be nasty. So we have a couple of autopilots on board, primary autopilot and backup autopilot. Autopilots can fail. They can and have failed for us, and both individual components or software. And so the fail-safe is monitoring via heartbeats and status, the two autopilots, and it will automatically switch over to a backup autopilot if the primary one fails. The main computing resource we have on the plane is a Panda board. That's this little board here. This is a dual-core 1 gigahertz ARM with a gig of memory and running Ubuntu Natty. This is the main mission control computer. It's got enough computing horsepower to do things like the image recognition, the camera control, the mission planning, all of that sort of stuff. It's connected to an SSD on the back here. SSDs are quite good for vibration in planes, better than having spinning rust in your plane. So sort of a 60 gig SSD pegged to the back of the Panda board, and some extra USB, lots of USB cables going all over the plane to various devices. Most of those lines you're seeing there are USB cables. A couple of radios. We have in our project, we've decided on 2 radio links, and these are the 2 primary radios that we're using in the plane. This is a 5.8 gigahertz Ubiquiti Bullet. It also runs Linux. And so this is, you can download the source firmware for this, which is really quite nice. As yet we haven't needed to modify it, we're just running the stock firmware, but it's nice to know that we could modify it, and we have considered the possibility of modifying it for some particular purposes. This will, at close range, do about 130 megabit, but we set it to the minimum bandwidth and the maximum range that for this competition, which we'll set it to about 1.5 megabit. With a cloverleaf antenna, which I don't have here, attached to it. And also we have a 5.8 gigahertz amplifier, which I've got somewhere in my box. Anyway, we have an amplifier that we put on this in line with the antenna, and that amplifier boosts the range so that we can get a solid signal at about 8 kilometres, which is what we need at the 5.8 gigahertz, giving us about a 1.5 megabit link for imagery, videos, that sort of thing. This radio is the complete opposite. This radio is made by RFI in Perth. We got these second-hand, and we were very lucky to get them. And they're run in the 900 megahertz, so about 915 megahertz range, the ISM band. Extremely sensitive radios, very long range. So we found that with this radio, and even if we had the antenna at the other end sort of stuck into the grass in the ground, or pointing totally the wrong direction, completely solid link. We run this link at 9600 baud. So this is our reliable link to try to, in case in the rules, if you lose link for a few seconds, you have to take drastic action. We want to make sure that this stays up all the time. And so we run everything over both links, except for things like images and photos, video. And our ground station automatically monitors the dual links and switches between the links appropriately. This, however, one slight problem is it's quite heavy with its associated cabling and stuff, and the antenna, this is about 1 kilogram of radio, nearly about 900 grams or so. So it's a very heavy radio. We are also looking at an alternative, which is an extremely small little radio, and you may have seen me playing around with the little bits of electronics in my laptop this week. That's the alternative radio we're looking at, which is a little Hope RF, and that is, well, it's about the size of my thumbnail, roughly, and it's actually an extremely sensitive, good long-range radio. We've ended up writing our own firmware for it, adding frequency hopping, spread spectrum capabilities to it for our project. Then we have the cameras down the bottom there. As I said, we've got 2 cameras. One is a infrared camera, grayscale output. They're a couple of megapixel, these cameras. Sorry, 1.2 megapixel. And then a colour camera as well, so 1 colour, 1 infrared. The reason for the infrared camera is that Joe conveniently has a 50 watt IR source with him. In fact, 50 watt IR source isn't as impressive as it might sound, because once it gets through the IR filter they've got, it's in fact just a 50 watt halogen bulb stuck below an IR filter, and only a few watts actually get through that filter. The amount actually getting up to the sky isn't very impressive at all, and a small amount of reflection off a t-shirt can be quite a bit brighter than the lamp, which is a bit of a problem. So it's various things we're doing with the imaging to do that. So colour cameras connected to the Panda board. And what else is on that diagram? That's about it. So that's our main avionics, a rough idea of what it looks like in theory. And this is what it looks like in practice. This is our avionics, or at least some of our avionics, stuffed into our senior Telemaster. So the blue light there is on one of the Autopilots, and then the red and green lights at the back are on one of the radio links. The Panda board in between doesn't have any lights on it. It's controlling the cameras, which are stuck underneath the plane. It gets rather messy, and one of the problems with the senior Telemaster is it's not big enough inside to have a good layout of all of our cabling and things. The much bigger Mugin that we're moving to for the competition is a much roomier aircraft inside. It's better for a reliable layout of your cabling and electronics. Okay, so autopilots. So here's a autopilot, there's another autopilot. You're welcome to come up and have a look at these closer later. The one on the top right there is this one, that's an APM-1. The basic set of sensors on these autopilots is the same. They've got the AVR 2560 CPUs, so typical Arduino style CPU, 8K of RAM, 256K of flash, 8 channels of radio control input-output, PWM or PPM input-output, 4 UARTs for serial, 3-axis gyroscope, 3-axis accelerometer, a 3-axis magnetometer, compass basically, 3D compass, a barometer for altitude, GPS, a pitot tube for airspeed, and a sonar for low-level altitude for landing, and all open hardware, open software. This all comes from a fantastic project called DIY Drones, which I'd highly recommend if you're wanting to get into autopilots and or just stabilizers for RC flight, or quadcopters or whatever. And the complete open hardware community, all the schematics for these boards are available, and in fact they encourage other people to make the boards if they want to. All of the software is open just in a Git repository, and a great community of volunteer programmers. So I'm one of the volunteer programmers for the project. I've been doing a lot of coding of this thing over the last year. So there are a couple of little autopilots, and there's some particular features of the sensors that are, make this one a little bit more appropriate for us than the other one, but they provide the same basic capabilities. Later in the year, the project is going to be moving to an ARM-based autopilot, mostly because 8 kilobytes of RAM is a pretty big restriction. We've got about 57,000 lines of C++ code jammed into this autopilot. According to the Arduino folks, we're the most complex Arduino program ever written. And it shows, and we're counting how many bytes of memory we've got left. So moving to an ARM CPU will be a real blessing. Onboard computer, as I showed you the Panda board here, dual core 1 gigahertz ARM, SSD storage, Ubuntu Natty, and lots of Python scripts. A little bit low on time, so I'll skip past that. The 2 radio links I've mentioned, we've got a high bandwidth link, the Ubiquity link, and then we've got the lower bandwidth RFI radio, and then the little tiny Hope RF radio. And this is Jack Pitter, who's our main aero modelling expert. We're doing radio testing there over an 8-kilometre range with a 20 dBi phased array, 5.8 gigahertz antenna there that we were donated. We were very lucky about donations to the project. That little donation came when we bought another thing from a an electronics store in Australia, and they decided to throw in this antenna with a little note on it saying, "Thanks for rsync." So it was really cute. Apparently they use rsync over some of their links. Anyway, so this is our team out with our Joes. We have some fake Joes. We tried to get clothing that matches approximately what we think Joe's going to be wearing. And the computer vision is an important part of the project. We've got point grey chameleon machine vision cameras, one IR, one colour. We take about 8 frames a second, 70 microsecond exposures approximately, and we don't have this as yet, but we're going to have a gyro-driven servos to point the camera always straight at the ground. Lots of drivers and software we had to write ourselves, geo-referencing code, image recognition. We had to write new drivers for the cameras because the existing drivers wouldn't drive 2 cameras reliably fast enough on this ARM board. So we wrote complete new drivers. This is an example image we've taken, and I'll just show you roughly what we do with the image recognition. So this is a debayed image that comes from about 100 metres altitude above our search area. And there's 3 little white blotches some of you see if you're in the front row anyway. Up the back, can you see the 3 little white blotches? Excellent. Those 3 little white blotches are, that's those 3 dummies that you're seeing on the ground there, right? And that's what they look like from 100 metres. And you just got a few pixels after the debayering, because we do a 2-to-1 scaling during the debayering because it's fast that way. Debayering's too expensive for us to do properly at the frame rate we need on the CPUs we've got. So we do a 2-to-1, so we end up with 640, 480 images. So that's what goes into our image recognition algorithm. And the first thing we do is RGB quantization. So we basically quantize it down to 3 or 4 bits along each of the colour axes, red, blue and green axes. We end up, if I unquantize it again, that's the result of that image after it's been through the quantization stage. At that point, we do thresholding. We're basically thresholding on brightness and colour space. Now, if you are towards the front row, you may notice some speckles on the right-hand side because you get a little bit of extra above the threshold, those little speckles. So we have an additional phase through the image recognition algorithm where we do a thing called neighbour expansion, where basically you take the probabilities of local pixels and combine them with surrounding pixels to produce a grouping. So there's our 3 groupings for our 3 Joes. And finally, we do final selection and geo-referencing. So we take the attitude information from our gyros and the autopilot, and we do some trigonometry to calculate the position of Joes on the ground so we can work out where to drop the bottle. So that's how all the image recognition works. Bottle drop, this is our bottle drop mechanism. Basically, little servo release, GPS for location from the image recognition, calculated trajectory. Main thing is repeatability, because you need to be able to drop it in the same spot every time. If you drop it off a bit, you can always offset. So we need a really repeatable drop mechanism, and we're still perfecting our bottle drop mechanism. Geo-fencing is something we've added recently. You have to have geo-fencing for the competition, so I decided to add it as a general feature to the autopilot for the RC community, because when you learn to fly, a lot of people, when they're learning to fly, crash their planes. The geo-fencing feature we've added we use for pilot training, where you set up a geographic box. In this case, the white line there is a boundary around the airfield, plus a minimum and maximum altitude. And if you stay within that box, you have complete manual control of the aircraft. As soon as you hit that boundary, it takes over and flies you back to the middle and asks you, do you want to take over again? You then take over flight again. And the idea is to create, if possible, an uncrashable RC plane, which is great fun. So the geo-fencing has been a real hit with the Autopilot, and a lot of people interested in it in the community for training pilots. This was our youngest test pilot. On Christmas Eve, he turned up at our local flying field, and I'd just finished the geo-fencing code, so I asked his mum, would he like to have a fly, and it made his Christmas. So that's my Skywalker on the road on the right there. So as a 5-year-old, he was flying my plane around the sky, doing circuits, and of course he occasionally made mistakes, and the geo-fencing took over and flew him back to the middle, and he could then take over again. And if a 5-year-old can fly the plane, then you've really succeeded. So that's Wilson, by the way. This is our ground station. You may notice that I've got a rather strange laptop here. right? This is an old ThinkPad, and it's missing something. Who can tell me what it's missing? Right, it's missing the back. So basically, we wanted a sunlight readable ground station. So if you normally use a laptop out in the sun, it's completely useless. You just can't see anything. The brighter the sun, the less you see. So the simple solution that Nick at Make Hack Void came up with is you cut the back out of the laptop, right? Slice it out, and then the sun streams straight through the LCD, and you end up with a fantastically clear, vibrant, full colour display. And it's brilliant. Absolutely brilliant. So that's our ground station solution. Highly recommend it if you've got an old laptop. Do be careful though. Somebody else who tried the mod tried to get the last few pixels at the bottom clear and managed to puncture the LCD, and that's bad. So you don't use your wife's favourite laptop when you're trying this hack. Lots of ground station software, MAV proxy, Q ground control, APM planner. You can see the various bits of software there. That's how we're controlling it on the ground. This is roughly the sort of search mission we're going to be doing. 150 metre wide strips, because that's the width of the Canberra at about 120 metres altitude. 50% overlap between strips, an interleaved pattern. This is a non-interleaved pattern I'm showing because I just happen to have the image of it. About a 30 metre per second cruise speed, so 100 kilometres an hour or so. 68 kilometres total flight, controlled completely by Python scripts running on the Panda board. All open source, of course. Simulation regression, we've spent a lot of time on simulation, building software simulations at the register level simulations of our sensors, which allows us to run software in the loop and also hardware in the loop simulations, so we can fly complete missions. And in fact, we now automatically fly missions on every Git commit. Whenever the Git commit goes in, it goes and flies a mission. So I could flick over and show you, there's our auto test software, and you can see the last run was today at 1:05 in the morning, and we could then say, okay, we want to see the track of that, and it will then, if I've got a network link, it'll bring up and show that's the path that it flew for that last mission, which is really cute. And that allows us to then see exactly how it's behaving and ensure that every Git commit that we do actually works. We do about a 1 kilohertz simulation. We also have Python physics models for multicopters, for testing the multicopter code in Arducopter. And we do a lot of this sort of simulation work. The protocols, the plane talks to the ground station via a protocol called the MAVLink protocol, where we basically have XML files. I can show you roughly what those XML files look like. Here's one of the XML files, if you can see it. They define all the parameters that we can send from the plane to the ground station and commands from the ground station up to the plane. We then have a Python script that compiles the XML file, which generates very compact C code for microcontrollers and also Python code for our ground station. So we generate all that from the XML files, and then that gives us it also gives us lots of tools for graphing and analysing and playback, so we can take a flight and play it back, and we can slow it down, step through it frame by frame to see exactly how the plane was behaving, and we see a real plane on the screen when we're playing it back. So when it hit the tree and went like that, which it did, then we can see it sort of hanging there in the tree in the simulator. So that's sort of the main protocols. I can show you roughly what that looks like. So if I do that, that's a MAVLink log dump. If I just expand that up a little bit so maybe you can read it, and you can see things like we're looking at how much memory is free, so 1.1 kilobytes of memory currently free on the CPU, the GPS status, number of satellites, all the waypoint information, the navigation controller, all of these sorts of things are then recorded in our logs, and then we can play back those, and we can do things like graphing it. So if I ask to take that flight log and graph the ground speed and the airspeed from the PITO, and then you can see that that's our ground speed versus our airspeed, and we can then go and start doing quite detailed analysis of the flight to see if there's any tuning that we need to do. So that's that. So unfortunately we're running out of time, so I'd like to have a few minutes for questions. If you want more information about what we're doing in our project, then CanberraUAV there and DIY drones and our auto test system plus our photo gallery. And I thought I'd briefly fire up the plane so you can hear some beeps and things. You know, this isn't a real talk unless it's got some beeps and boops going on. So if I plug that in, I really should have the ground station running at this point. So let me just go back and run the ground station. And let's see if we can get some sound out of it. Our ground station, by the way, its main output is text-to-speech. It's actually sound that comes out of it announcing what it's doing. And that's incredibly useful because you don't want to be looking at a ground station. You want to hear it saying things like distance to waypoints and altitude and all this sort of thing. So it's currently calibrating its sensors.
Link 1 down.
Okay.
No heartbeat.
Up. Okay, hopefully,
no heartbeat.
Hopefully it'll get the link back soon.
No heartbeat.
Okay, it's warning me that it hasn't got a radio link at the moment. I don't know why.
Heartbeat.
So I think I'll just tell it to shut up for a second.
No heartbeat.
And great. Okay, so let's now fire this up. So what I've got here is a little RC controller, and now let's see. I haven't actually. Now, why is that not coming on? Okay, firing up again. All right. Wait for it to finish firing up. Okay. Oh, good. Okay, there we go. Great. Oh, yeah. Oh, yeah, I set this thing down to a really low baud rate. Okay, I could turn on sound. You'll probably hear some things. Let's see whether it can... All right.
Mode stabilize.
Great. Okay, mode stabilize. So what you're seeing there is this is the little autopilot here, and you see it's got a nice engine. We can possibly take it out for a fly later if anyone wants to go. Oh yes, hey, that's good. It comes with about a 150 watt motor, but I wanted to go a bit faster, so I put a 450 watt motor in it, which. So it does, it really goes along quite fast. So the little autopilot there connected to one of these little Hope RF radios. And if you can, up the front, you'll probably hear the servos going. So as I'm rotating it, the servos are automatically compensating. And so to basically keep it in level flight, if I point it upwards, it tries to put the elevators down, it puts the elevators up, etc. And then I can flick it into different flight modes. It'll stabilise in different ways. And plus we have, control
Mode
like that.
FBWA.
Yep.
Mode stabilize.
Etc. Okay, so that's basically the way it works. So I believe we're just about out of time. So is there time for a couple of questions?
Hello, testing. There's plenty of time for questions, so rather than me running around with a microphone, just shout them out and we'll repeat the question.
Yep, okay, I'll repeat the question if you shout it out. Yep.
Did you consider it, so the search pattern, is that mandated by the rules?
No.
So did you think of going from a higher altitude and then zeroing in?
Okay, so the question is about the search pattern, whether the particular search pattern is mandated by the rules. No, it's not. The search boundary is mandated by the rules. You can use any search pattern you like. There are, and some of the teams are planning to do a 1,500 feet initial survey of the area. You can't fly above 1,500 feet. In fact, you can't fly above 400 feet without tower permission, and you're not guaranteed to be given tower permission. But a lot of teams, in previous years, people have been given tower permission, so you could plan to initially do a survey at 1,500 feet, and then to go down and look at a particular location. With our machine vision cameras, the way our algorithms work, we're better off staying at roughly the same altitude because we do have time to do complete coverage. About 45 minutes it'll take us to cover the entire area. So we didn't think it would be a win. Basically at 1,500 feet with the size of lenses that we've got on the camera, Joe would be about 1 pixel. And that's really a little small to spot for a machine vision algorithm. Some other people have got extremely expensive cameras. There's one team that reputedly has a $20,000 camera on board, so they've obviously got some sponsorship. They can perhaps do a little more zooming in, but most of the teams, I believe, are doing manual recognition of Joe, automatic flight, manual recognition. We're aiming for the extra points of doing completely automatic recognition, automation the whole way, and that changes the approach that we're doing for the search pattern, etc. Yep. Next question.
Down the back.
So I've got a couple of questions.
Yep.
What's your camera resolution?
It's 1280 by 960.
And you said you're doing all your vision stuff in C, so you're not using the onboard image?
We're not using the DSP yet. There's got a TI DSP on board the Panda board, which we could potentially use. I'm sorry?
You've also got the Power VR that you could be doing GL.
Okay. I don't know much about those parts on the Panda board, and so we've been doing it just in C at the moment. If we find we can't do our image recognition well enough in just straight C code, we may look into those DSPs, and I was asking Dave Mandela a little bit about those. If you know something about how to use those libraries, in particular APIs, etc., for getting at them, then I'd be interested in hearing about it. But we think we can do it sufficiently with the CPU that we've got available with the 1 gigahertz core.
You've also got a stereoscopic 1920 by 1080 H.264 hardware encode that you could be using.
Yeah, the H.264 encoding really doesn't help when you're looking at only a few pixels, because basically it will be compressing the what's at the target you're looking for into noise. So we keep the images. If we wanted to do H.264 type encoding, that would be for sending it to the ground station to give us an overview. But for the actual image recognition on board, it really wouldn't be worthwhile. I'm still interested in knowing if it's actually, I didn't know it had hardware H.264 encoding. If it does, that's interesting for sending images to the ground station. I'd love to talk to you about it later if you could possibly come up. Yeah.
Question at the front here.
Yep.
What are you doing to handle wind?
Okay, how do we handle wind? Well, first of all, we'll put wind into our simulator. So we've got randomised wind generation in our simulation, so we make sure we handle it. We've got things like cross-track error correction in the Autopilot, which basically allows it to keep on track and slew the plane appropriately for wind. Plus, the stabiliser automatically copes with gusts pretty well. It's adjusting the servos at 50 hertz, and it tends to do pretty well in wind, better than I can as a pilot. So we have to cope with up to 20 knots for the competition. At 20 knots, it's going to be damn difficult, particularly the automatic takeoff and landing, because the automatic takeoff and landing at low speeds, wind is much more problematic, and we're not at all certain we'd be capable of doing that. If we don't think we can, we could switch back to manual takeoff or landing if it was really high wind, particularly landing in a crosswind. And in that case, we'd lose the points for the automatic takeoff and landing, but we'd still be able to do the automatic search in the wind, we think. Yep. Next question? Yep, in the middle there.
Does the controller handle things like anti-wind-up?
Anti-wind-up?
Yeah.
What do you mean by anti-wind-up?
Like saturation of all the controllers?
Oh, right, okay. The core of the Autopilot is basically a set of PID loops, cascaded PID loops. And I assume you mean that the I value in the PID loop starts saturating, get to an I max, that sort of thing? Is that what you're talking about? Yeah, so that can happen. You set an IMAX basically. So it's a PID with limits on the integration component in the controller. Basically you set that to reasonable limits in order to say, you know, you don't compensate by more than 20 degrees, 30 degrees or something like that. You have to know roughly what those limits are based on the expected maximum wind speed that you want to cope with, turbulence, shifting of weight inside the plane, that sort of thing. We'll have to, for example, when the bottle gets dropped off, that's a small loss of weight. It'll change the balance of the plane slightly. In our big plane, hardly any difference at all. If you dropped a bottle off this thing, it would, change completely the way it flies. So yeah, that's coped with in the core algorithms of the cascaded PIDs in the Autopilot. Yep. Down here?
Yep. So if a 5-year-old is flying a plane,
yep.
Is he or she capable of putting it into a stall or other failure conditions? And can you cope with it if it happens?
Yes, so when the 5-year-old was flying the plane, could they put it into a stall condition and would it cope with it? In fact, he did put it into stalls, he did things like drop below 30 metres. I'd set a 30 metre minimum altitude in the Geo-Fencing, and as soon as he passed the 30 metre mark with the barometer, it immediately took over and went into a mode, what's called guided mode, where it flew back and started loitering in the middle of the field, ready, and then you click a button. Basically, there's a little spring-loaded switch here down the bottom, and that spring-loaded switch says, I want to take over again. It only works once you're back inside the fenced area. Right, if you're outside the fenced area, it says, nope, you can't take over again unless you use this switch to turn off geofencing completely. And he didn't. And so...
So you kept a strong eye on that switch.
But the main problem that, that kids often have, was, which also Wilson had, was he tended to, when he wanted to turn right, he'd look down at the transmitter to turn, and then he'd look up and where's the plane? Because when a plane is a couple of 100 metres away, it's very hard to spot it, and that's why my planes tend to be fluorescent pink and fluorescent yellow and things, because it's easier to spot them in the sky. And the plane he was flying had fluorescent pink along the bottom of the wings to make it a little bit easier. But yes, it does cope quite well. It's not perfect. You can still crash it. We demonstrated that on Wednesday morning, flying it out here, and it is possible to still crash the plane, but it's much less likely. It does rescue it from a very wide range of conditions. And we've tried things like, I tried inverted flight, flying it upside down along and then diving it at the ground while upside down, and it flipped the plane right way up and brought it out of the dive by only a couple of metres off the ground at the lowest point, but it does work.
One more question, I think.
One more question up the back here. Yep, somebody there?
You said before you had to demonstrate the crash on demand.
Yes.
Will the airframe survive that demonstration, or do you effectively take two airframes to the competition?
No, I was being a little bit overdramatic. The way they demonstrate it is they actually drive the vehicles across the emission boundaries and check that all the servos go to the right position, the surfaces go to the right position when you drive it across the emission boundary. We'll also be demonstrating it in the simulator, and we'll also be demonstrating it in a real aircraft. I have demonstrated it many times, except the action it takes when it went across was to fly back to the middle. So now that Wilson was demonstrating it for me when he flew across the mission boundaries, when we defined those small boundaries. But no, you don't have to actually destroy the aircraft except in the actual competition, and during the actual competition you do have to destroy the aircraft if it goes outside the boundary. Yep. Okay, well thank you very much. And if any of you want to know more about these things, you're welcome to come up and talk to me and have a look at some of the equipment. And we might even take it out and have a fly of it. So just be aware that there's a very good chance we might crash it, because that's error modelling.
Thank you very much, Andrew. You've set yourself quite a challenge across many disciplines and many ideas and technologies in this approach, so quite a challenging exercise to be involved in. On behalf of Linux Australia, I'd like to present you with a little token to thank you for your talk.
Thank you.
Thank you very much.